Okay, so we're going to look at buffers today, and just to start off by way of understanding what a buffer is, imagine that you've got 1 decimeter cubed of pure water. So we would imagine that it really is pure, the pH should be pretty close to 7. And then we're going to add 1 drop of sodium hydroxide. 1 drop has a volume of about 0.05 of a centimetre cubed, and the sodium hydroxide has concentration 1 mole per dm cubed. And let's do this at 25 degrees. So Kw is 10 to the minus 14. So what I'd like you to do is to calculate the new pH of the solution after we've added the sodium hydroxide. So pause the video if you want to work it out yourself. So the calculation would go, well, let's work out the moles of sodium hydroxide first. Moles of sodium hydroxide, CV over 1,000, well, concentration's 1, so it's just 0.05 over 1,000, which is just 5 times 10 to the minus 5. And since there are 5 times 10 to the minus 5 moles of sodium hydroxide are in 1 decimeter cubed of pure water, the concentration will therefore be 5 times 10 to the minus 5. And since the concentration of sodium hydroxide is 5 times 10 to the minus 5, the concentration of OH minus will be 5 times 10 to the minus 5, because sodium hydroxide is a strong base, so it's completely dissociated. Okay, so now we can work out the concentration of H plus, which is 10 to the minus 14 Kw over concentration of OH minus, which comes out as 2 times 10 to the minus 10. And then if we hit the log button and change the sign, the pH comes out as 9.7. Now, I've actually had a student in a previous class look at that value and say, well, I've got 9.7, but I think it's wrong. Why do you think it's wrong? Because it's too big. How can 1 drop of solution change the pH from 7 all the way to 9.7? 1 drop. Well, it's because OH minus ions change the pH an awful lot. That's the nature of pH. It's especially around a pH of 7, very, very small additions of H plus or OH minus make a huge difference to the pH. Now, that's not really a problem necessarily in the lab, it's just 1 drop of solution, right? But in a living system, it's a huge problem, especially when we look at enzymes. And if you've done a bit of biology, you'll know that enzymes have an area of effective activity which is very pH dependent. And if I go outside of that pH, the effectiveness of the enzyme drops off very, very quickly. Or even leads to the enzyme being completely denatured, which means that it can't do its job, which means the cell malfunctions, which mean it dies, which means the organism might die. So that's obviously a dire situation. So very small changes in pH. So if you drop a small amount of chemical into a fresh stream, for example, that can have a devastating effect on the local wildlife in that environment, because you're suddenly flipping the pH to an extreme. So that's why we need buffers. So buffers resist change in pH. resist change. Doesn't mean they don't change at all, but they resist change in pH for small additions of acid or base. In other words, buffers won't stop the pH change completely, and of course if we pour in a bucket full of acid, the pH is still going to go down. But if we add small additions, 1 drop, we'll see a very different change. It certainly won't be 9.7. It might go from 7 to 7.02, but it wouldn't be such a big change as that. So buffers resist change in pH for small additions of acid or base. And there are lots of natural systems which are buffered. Blood is buffered. Seawater, interestingly, has buffering chemicals. And the cytoplasm of cells is buffered. So again, the pH stays within very, very tightly controlled parameters. Sorry, that's the wrong question. We've already done what is a buffer, haven't we? The question, how do I make a buffer? Well, it's quite easy. We need to start off with a weak acid and add a salt of that weak acid. Of course, that would make an acid buffer. I'll come to a base buffer in a moment. So a weak acid, so an example of that would be ethanoic acid. And a salt of that weak acid, well, sodium ethanoate. So if I take some ethanoic acid, add a couple of spoonfuls of sodium ethanoate, I've got an acid buffer. Weak acid and salt of that weak acid. Now, you don't have to understand the workings of base buffers. We're going to focus all our attention on acid buffers, but you should know how to make one. And the ingredients are very similar to the acid buffers. So a base buffer is a weak base and a salt of that weak base. Okay, so a weak base, something like ammonia or ammonium hydroxide in solution, and ammonium chloride would be a salt of that. So again, a mixture of those two chemicals, or dissolve some ammonium chloride in some ammonia solution, that will give us a base buffer. Obviously acid buffers have pHs less than 7 and base buffers have pHs greater than 7. And in today's modern world you can buy buffer tablets. So you get a box of small tablets. They look a little bit like vitamin pills, and you drop them in water and stir them and dissolve them, and then that makes up the buffer to a very specific, precise pH. So how does a buffer work? Well, sticking with the acid buffers, although the base buffers obviously work in a similar way, if I put my ethanoic acid and my sodium ethanoate into distilled water, they will both dissociate, but they dissociate in different ways. The ethanoic acid is a weak acid. So when I write the reaction for dissociation, I use a reversible arrow to indicate that it can reach equilibrium. And we imagine that in solution, most of my ethanoic acid, about 99% of the molecules, will remain as ethanoic acid molecules. Only about 1% dissociate to form ions. And remember, it's only the H+ ion that is acidic. ethanoic acid molecules, CH3COOH molecules, are not acidic. They obviously are when they dissociate in water, but the molecules themselves are not acidic. It's only H plus that gives us acid. So it's a weak acid because it's partially dissociated. Sodium ethanoate is a salt. Salts dissociate completely in water, so we use a straightforward reaction arrow. We make the ethanoate ions again and sodium plus ions. Now if we just think about for a moment what's actually in the solution. So we just said that very little of the ethanoic acid dissociates. So in other words, there's lots of ethanoic acid molecules in the solution. The ethanoate completely dissociates, so there is lots of ethanoate ions in the solution from the sodium ethanoate. And there'll be lots of sodium ions as well, but I'm not so interested in those. Okay, so there's none of that, lots of that too, lots of that, very little of that, very little H plus. Okay, so now let's think about what happens if we add H plus. Well, we know from Le Chatelier that any change to the conditions will result in a shift of the position of equilibrium that minimizes that change. We've got a delicate balance here between the molecule and its dissociated ions, one of which is H plus. So if I pour in a bit more H plus, what's going to happen? Well, Le Chatelier says the equilibrium position will shift to the left to remove some of the added H plus and restore the equilibrium. So as we add the H plus, the equilibrium position shifts to the left, removing the extra H plus. But hang on a moment, if I stuck in a whole load of H plus, it's got to react with something to make the ethanoic acid. Oh, well, that's the clever thing, because of course we have lots of ethanoate ions supplied by the salt for any extra H plus to react with. So even if I put in way more H plus than the ethanoate supplied from the ethanoic acid, it doesn't matter. There's always going to be plenty of ethanoate from the salt. So reacting the added H plus with ethanoate ions from the salt. Okay, what happens if we go the other way around and add OH minus? Well, we know OH minus reacts with H plus. So the OH minus will react with any H plus ions it finds and make water. Of course, that's in equilibrium as well, but that equilibrium is way over to the water side to the tune of 10 to the minus 7 moles of ions compared with 1 mole of water. So so we add the OH minus, it's going to react with the H plus. That's going to remove it from the equilibrium here, and then of course the equilibrium will shift to the right to replace the lost H plus. That can happen because again we've got lots of acid molecules, so we're never going to run out of those in order to restore the H plus. So in this case the equilibrium position shifts to the right to restore the OH plus. That is removed. Okay, so both ways, it's the equilibrium that helps us out, it's Le Chatelier that helps us out. Add H plus, we'll use it up using the ethanoate. Add OH minus, that'll take away the H plus, well, we'll make more from the ethanoic acid. So either way, that H plus gets restored to more or less its original level. Okay. This is a little bit of a roller coaster ride and involves quite a lot of maths, but hang in there. If I want to find the pH of a buffer solution, well, remember, I can write an expression for the equilibrium constant Ka for an acid, which is the concentrations of products over the concentration of a reactant. Now you might remember when we were finding the pH of a weak acid, we made some assumptions which related to how acids dissociate, and we're going to make some similar assumptions today, but importantly different. Let's start with one of the same assumptions, which is that the ethanoic acid dissociates so little that we can assume that the concentration of CH3COH molecules is still the same as the concentration of the acid. In other words, the number given in the question, 0.1 molar, whatever it is. The other assumption is that the concentration of ethanoate ions, well, the acid dissociates very little, but the salt dissociates completely. So most of the ions in solution are going to come from the salt. So let's ignore the small 1% error of the ions from the acid and pretend they all come from the salt. Okay, now if I rearrange that, I've got, sorry, not rearrange it, if I substitute those in, I've got the concentration of the salt times H plus over the concentration of the acid. Now if I rearrange it to make H plus the subject, it will be Ka times the concentration of the acid over the concentration of the salt. And I've arranged it like that for a particular reason, which I'll come back to in a moment. Okay. So that is our last formula that we need for this topic. We've done calculations of strong acids, strong bases, weak acids, and now buffers. So those 4 calculations are going to be coming up in the exam. Okay, let's do an example. We're going to add 12.6 grams of sodium ethanoate is added to 1 decimeter cubed of a 0.1 mole per dm cubed ethanoic acid solution. Oh, and we need Ka, which is 1.75 times 10 to the minus 5. Okay, so let's use our buffer formula. Concentration of the acid is given to us in the question. There it is. Concentration of the salt, well, we're going to have to work that out. So moles of salt is 12.6 over the formula mass of sodium ethanoate, which is 82. gives us 0.154 moles of salt. Of course, that's moles. It's very important you don't confuse moles and concentration in these calculations. In this case, 0.154 moles is in 1 decimeter cubed, so that will give us a 0.154 mole per decimeter cubed solution in this case, because we've got a decimeter cubed. So concentration of H plus will be Ka times the concentration of the acid, that's 0.1, over the concentration of the salt, 0.154, which gives us 1.14 times 10 to the minus 5. Hit the log button for that, and the pH is 4.94. Okay. Leave my buffer formula there and do another example. Calculate the pH formed when we add 25 centimeters cubed of, I'm trying to read this off the screen, 0.1 mole per dm cubed ethanoic acid is added to 25 centimeters cubed of 0.1 mole per dm cubed sodium ethanoate. Okay. Obviously they're the same volumes and the same concentrations. Now that means that when we've poured them in together, we'll have 50 centimeters cubed, and the concentration of each solution is going to be, well, it'll be 0.05, won't it? Concentration of each solution. What happens to this equation when these concentrations are the same? Well, when the concentration of the acid is the same as the concentration of the salt, this part of the equation just sort of disappears, and H plus equals Ka. And this has a special use, which we'll come to later. The pH will become the same as the pKa. So Ka was 1.75 times 10 to the minus 5, so pKa is just 4.76, isn't it? Seem to remember. Okay. So firstly, notice that the questions become quite trivial. You'll see this in exams. You'll get a buffer solution question, and it's only worth 2 marks. 2 marks, because all we've done is really notice that they're the same, and then hit the log button. So there's not an awful lot to do there, compared with quite a lot more work here. And buffer questions are going to get much more weighty than this, I'm afraid. But this will become important when we go back to looking at titration curves. More on that in a different video. Okay, let's do a fun buffer question. I realised when I was at school that whenever teachers talked about an interesting question, they always meant hard. So calculate the pH of the buffer formed when I add 10 centimeters cubed of 0.105 mole per dm cubed sodium hydroxide. (25 cm cubed) of 0.1 mole per dm cubed ethanoic acid. Okay, Ka 1.75 times 10 to the minus 5. Right. The first thing to notice here is I've not added a salt to my weak acid. I've added a base. But What happens when we add acids to bases? They react to make salts and water. So as soon as that sodium hydroxide hits the acid, it's going to react. A quick look at the numbers, you'll see I've got way more acid than base. So all of that base is going to react and it'll all turn into salt. So let's just do moles equals CV over 1,000. It's going to be 105 times 10 to the minus 3 moles of acid. So that'll be 25 times 0.1 CV over 1,000 again, 2.5 times 10 to the minus 3. So what happens when these two are added? Well, again, all the base will turn into salt. So we can work that out. Moles of salt will be the same as the moles of base. It's fine. What about the moles of acid? Well, that 1.05 times 10 to the minus 3 moles is going to react with some of the acid. So the acid will have dropped now from 2.5 minus 1.05 to 1.45. Let's just keep our eyes on the prize. The two numbers we need are moles of acid. Sorry, not moles of acid. It's very important we keep our eyes on the prize. Moles of salt, there it is, and moles of acid. There we are. Okay. So those are our two important numbers. Now, I'm going to wheel out the buffer equation. Ka times acid over salt. Now, again, it's very important not to confuse moles, these are mole values, with concentrations. How do we work out the new concentration? Well, we divide by the new volume, which would be 35. So I could work out the concentration of the salt and the concentration of the acid. Two extra steps that I don't actually need, because let's see what happens. If I substitute those numbers in, I'm going to have moles of acid on the top, 1.45 times 10 to the minus 3, and I need to remember to convert it into concentration by dividing by its volume. And I'm going to put that over the salt, which is also going to have to be converted to concentration by dividing by its volume. Well, it's a buffer solution. I've got the acid and the salt mixed together in the same flask. The volume has to be the same. So V for buffer questions will actually always cancel. So I might put a /V in the expression there just to remind me that I know that these are moles and that's volume, these are concentrations. Obviously I haven't forgotten that, but actually it's just going to disappear. It's just going to cancel. So if I times my Ka, 1.75 times 10 to the minus 5, by all of that, that cancels to 2.42 times 10 to the minus 5, and then I hit the log button. Okay. So notice in the three examples that we've done, that was example 2, wasn't it? In the three examples that we've done, I've made the buffers in different ways. The first way, I added solid salt to an existing solution. The second way, I've added two solutions together. In the third way, I've added a small amount of base to an existing acid solution. All three of them make buffers. Now AQA are usually pretty fair about this. They normally say this is a buffer solution, or a buffer solution is made by, but They don't have to. They could just give you the information and tell you to work out the pH and expect you to recognize that a buffer is made. Now, that's fine if you're adding acid to salt, but when you're adding base to acid, it's a lot less clear. And as we've seen in other partial neutralization questions, it could go the other way. I could have excess base. This could actually be a strong base question. So you really need to keep your eyes open and focus on the amount of base you've got and the amount of acid you've got and work out, which is bigger. In this case, acid's bigger, the base is neutralized, but it made salt, so it's a buffer question, and that can really trip people up. So one of the main problems with buffer questions is that students don't even use the buffer formula. They don't even know they're working out a buffer question. They do weak acid or strong base or something else. I hope you enjoyed that. Please like and subscribe, etc.